Have you ever really stopped to think about the chips inside, well, everything? Your phone, your computer, your car, they're all powered by these insanely complex circuits. We're talking millions, sometimes billions, of tiny parts all working together. I mean, how on earth is that even possible? Well, today, we're going to find out.
Okay, so really, how do you build a circuit with that many parts? I mean, can you imagine trying to physically arrange and connect millions of tiny little switches to make, say, a processor? Could you draw that out by hand? No way, right?
Well, the answer is you don't. You don't build it, you describe it. At least, not directly. See, the whole way of thinking about this had to change. Instead of trying to build the thing piece by piece, engineers figured out a way to just describe what they wanted it to do using a special language.
Okay, but before we got to that pretty elegant solution, the entire industry was just hitting a wall, a massive wall of complexity. We can call it the million gate problem. And yeah, just think about it for a second. Trying to use the old school manual design methods to create a chip with millions of logic gates, it was basically impossible. It was way too slow, you'd make a million mistakes, and it just couldn't scale up. The complexity was just completely out of control. So, it was pretty clear that something had to change. The industry needed a new tool, a totally new way of thinking about this stuff. And what they came up with, it's a lot like creating a blueprint for hardware. You know, just like an architect draws up a blueprint for a skyscraper before anyone lays a single brick. And that blueprint, it's written in something called a hardware description language, or HDL for short. And honestly, it's exactly what it sounds like. It's a special computer language you use to describe, in text, the structure and the behavior of an electronic circuit. This is the key. This is what lets designers finally get a handle on that insane complexity. Now, one of the heavy hitters, one of the two main HDLs out there, is called verilog. And get this, it was first introduced all the way back in 1985. And today, this whole idea, describing hardware with text and then having a computer automatically figure out the circuit, is pretty much the standard way the entire industry designs chips. All right, so what does this language of logic actually look like? Let's peel back the curtain a bit and check out the basic building blocks, the vocabulary and grammar you'd use to write one of these hardware blueprints. Okay, so first things first. In regular old binary, you've just got 0 and 1, right? Off and on. Well, Verilog takes it a step further. It has 4 core values. You've still got your familiar 0 for low or false, and 1 for high or true. But then you also get X for an unknown value, which, trust me, is super useful for finding bugs. And you have Z, which represents a high impedance or an unconnected wire. This helps you model what's actually happening in a real-world circuit. Now, the good news is, a lot of this is going to look really familiar, especially if you've ever seen any programming language. Verilog uses all the standard symbols for math, plus for add, minus for subtract, the asterisk for multiply. You get the idea. It makes writing the logic feel pretty natural, pretty intuitive. Okay, now here is a subtle but really, really critical detail you gotta know. Verilog has 2 different ways of saying equals. The double equals sign, that's for logical equality. You use this when you're describing the actual logic that's going to become hardware. But the triple equals sign, that's for case equality. It's much more strict because it can also check for those weird X and Z states we talked about. This makes it perfect for when you're testing and simulating your design to make sure it's perfect. All right, so we've got our basic values and we know how to do some math, but how do you actually organize all this stuff to build something complicated without it turning into a complete spaghetti mess? Well, the answer is a brilliant concept called modules. So what's a module? It's the basic building block in Verilog. And honestly, the best way to think about it is like a Lego brick. It can be a simple single 2x4 piece, or it can be a whole pre-built assembly you made by snapping a bunch of smaller Legos together. And this is where the real power comes in. The magic of modules is something called abstraction. A module basically hides all of its internal, complicated guts. It just shows the outside world a simple set of inputs and outputs. So as a designer, you can just grab a module and use it without having to know or even care about every little wire inside of it. It's a game changer for managing complexity. And the actual structure of a module in the code? It's super straightforward. First, you declare it with the module keyword and give it a name. Then you list its ports, all the inputs and outputs. After that, you write the actual logic inside that makes the magic happen. And finally, you just wrap it all up with an end module keyword. That's it. Okay, let's look at a really quick example. This is a multiplexer, or MUX for short. So you can see it has three inputs, A, B, and a selector called cell. And it has one output, Y. Now, all the logic is in that one single line of code there. That's a conditional assignment. It basically says, hey, look at the cell input. If cell is true, or a 1, then make the output Y equal to A. If it's not, make Y equal to B. It's like a simple switch. Super simple, but incredibly powerful and totally reusable. Okay, so this is the million-dollar question, right? We've written a text file. It's just code. How does that description turn into an actual physical piece of silicon that does real work? Let's follow the journey from code to silicon. This is the part that feels like actual magic. The process is called synthesis. And basically, you feed your verilog code, your blueprint, into a special piece of software. This software, the synthesizer, reads your description and automatically translates it into what's called a netlist. And a netlist is just a super detailed map of all the logic gates and exactly how they're all connected. So boom, it just turned your text into a real circuit design. From that point, you've basically got two main paths you can take to get to real physical hardware. Path number 1 is an FPGA, which stands for Field Programmable Gate Array. Think of it like a blank slate chip that you can program to become any circuit you want. It's super flexible and amazing for prototyping. Path number 2 is an ASIC, or Application-Specific Integrated Circuit. This is a custom-built chip designed to do one and only one thing perfectly. It costs a ton of money to design up front, but if you're making millions of them, they end up being way cheaper, faster, and more power efficient than an FPGA. And that's the journey, from a simple text file all the way to a complex piece of silicon doing work. It's this incredible system that allows even a single person or a small team to design hardware that's just mind-bogglingly complex. It really democratized the whole process. So that leaves just one last question for you. Now that you know how the blueprint works,